Hello students, Professor Gray here. We need to talk about separation of mixtures. Now, just to remind you of the types of mixtures that we've seen so far in this class, the first is a heterogeneous mixture, and this is a mixture with a non-uniform composition, meaning you have two or more phases that remain separate and keep their physical and chemical characteristics. That means that you will have a visible interface, and the interface is the boundary between one substance and another substance. So if we take a look at oil and water, for instance, what we'll have is the oil on the top there and the water on the bottom, and you will definitely see the interface, which is right here, and that's where the oil ends and the water begins, or the water ends and the oil begins, however you want to say it. And if you take a sample from up here and a sample from down there, you will have definitely different chemical and physical characteristics in those two different substances. Over here is a few examples of other heterogeneous substances. So we have cereal and milk. You can definitely see the boundary between the cereal and the milk, where the piece of cereal ends and the milk begins. And if you took a sample from the cereal part and the milk part, you would find that those two different phases have different physical and chemical characteristics. Also, ice and soda, you can see the different parts. Soil, you can see the different parts in your soil. There's a few rocks. You guys can hear my cat in the background now. Sorry about that. The soil, you can see rocks and sticks and all that kinds of stuff. Now, sometimes the interface can't be seen unless you use a microscope, but that still qualifies as an interface. So if we're talking about blood, you would use a microscope and you would see the boundary between the red blood cell and the aqueous part of the blood, or the watery part, and you might see a white blood cell, that type of thing. Now, the other type of mixture that we've talked about are homogeneous mixtures or homogeneous mixtures. And these are mixtures of substances that exist in definite ratios, but they're not chemically bonded. And that means that you are not going to see an interface, okay? So no interface. So here are some examples over here. So if we talk about air, what we've got, let me put some air in a beaker here. You've got molecules of oxygen and molecules of nitrogen, and both of those substances are diatomic molecules, which we talked about in chapter 1. So they come in twos, and we also talked about those in chapter 2. You also have a little bit of argon and CO2, but you can't, with your eyeballs or a microscope, see where the oxygen ends and the nitrogen begins, but you have all these components mixed together. Now, if you take a sample of your air from over here and a sample from over here, you will find that they have the same physical and chemical characteristics. Now, heterogeneous and homogeneous mixtures, how we separate the components of those is different. So some of our separation methods that we will use in the chemistry lab might be decantation, filtration, magnetic extraction. So if you've got a component that is attracted to a metal, you can run a strong metal through the mixture and the magnet will pick up all of the components that are attracted to the magnet. Centrifugation, you might use that if you've got blood and you want to separate the aqueous or the watery portion of the blood and then the blood cells. Chromatography, distillation, and evaporation. Now, the methods, the separation methods that we're going to see in this lab are decantation and filtration. And those are pretty good for separating heterogeneous mixtures. And we'll also take a look at chromatography and distillation, and those are quite good for separating homogeneous mixtures. So the first that's mentioned is decantation, and this is just a fancy word for pouring off one substance and leaving behind another substance. So say you have a sand and water mixture. So that would definitely be a heterogeneous mixture. You could see where the sand ends and the water begins. So what you would do to separate those two components is you would pour off the water and you would pour it down a stirring rod like this. So you'd have your water here and you would try to leave your sand behind over here. Now, what can you think of might be a problem with decantation for separating mixtures? Probably it's not a very good way to get a really good separation because a little bit of sand will come over into the water. And definitely when you have poured the water off and you're left with the sand over there, you're still going to have some of the water in that sand. You're going to have wet sand. So the next type of separation method that we use for heterogeneous mixtures quite often in the chemistry lab is filtration. So what we do is we get a ring stand, so that's this little stand right here, and we attach this little ring right here and we put a funnel in it. So there's your funnel and a beaker underneath it. And we put a filter in it and we use this round piece of paper right here called a filter paper. And you would fold it in half and then you'd fold it in half again so it was in a quarter. And then you'd pull towards yourself one side, which is going to end up right there, and push back the other three sides, and it's going to make a little cone. And you put the cone down into your funnel, and there you have your filter. So then you can pour your mixture into the filter. So another setup that you'll see for filtration, one that I prefer, is using an Erlenmeyer flask, so you don't have to use the ring stand and the ring. And an Erlenmeyer flask is different from the beaker in that the top of the Erlenmeyer flask is smaller than the bottom. So it looks like this, and you take the funnel and you can just set the funnel right down in the Erlenmeyer flask and put the filter paper in the top and then pour your mixture in there. And you can walk away and do something else while your mixture is filtering. Now, the fluid that comes down here, the liquid that comes down there, that's called your filtrate. And the solid that is left sitting up there in your filter paper, that's called your precipitate. I had to pause there because I forgot how to spell it, or it's also called the residue. You'll see both, okay? So now filtration is a better method of separation than decantation because the little holes in the filter paper are pretty tiny, so they capture a lot more of the solid up here than we would if we were doing decantation there. And you can get filter paper with different size holes. So you can get filter paper that has pretty small holes and catches a whole lot of the precipitate or the residue. Okay, so what happens if your particles in your mixture are super duper small? Well, then you'd probably have a homogeneous mixture because Remember in chapter 1 when we talked about the different sizes of the particles? That would make it to where it was so small that you couldn't see it anymore, and that would give you no interface. So, yeah, it probably would mean that your particles were going through the holes of even the filter and you wouldn't get any separation. So we have to use some different methods for homogeneous mixtures. And one of the most common ones is distillation. So we use a process of separating our components of our substances from a liquid mixture by using selective boiling and condensation. Okay, so what you guys are going to see in the lab is you're going to have a mixture of copper sulfate, copper 2 sulfate to be specific, and water. So your copper 2 sulfate has the formula of CuSO4. So we're going to have CuSO4 plus water, and this solution is going to be blue. It's not going to be yellow like the picture. Now, copper sulfate on its own is a blue solid, and then water is a clear colorless liquid. And then when we put them together, we get a clear blue solution. So what we're trying to do is we're trying to get back to the copper sulfate solid, and we're trying to do that by boiling off the water. So what happens is we have a blue solution here in this round bottom flask, and we heat it up, and water goes from liquid to what when it's heated up? To gas. So the water starts going up there, so we have H2O gas, and it's in the form of steam, and it comes on down into this tube right here. Now notice this funny looking thing right here. What this is a tube within a tube. So I probably shouldn't do that because then you can't see the tube within the tube. So let me erase that right there. Okay, so the steam goes down the center tube, the clear one inside. And what we do with the tube on the outside is we run cold water in here. And we keep running it through here, and then it comes out right here into the sink. So running it through there keeps it cold, and it keeps the inside tube cold. Now the steam that's coming through here, it's going to hit the cold glass on the inside tube, and when water vapor hits a cold surface, it does what? It turns back into liquid water. So what we have is that the steam that's coming over here hits the inside of that cool tube, that inner tube there, turns back into liquid water, and it drips on over here into the receiving flask. This thing right here is called the condenser. You can see that up there because it causes the gaseous water to condense back into the liquid. Now the water that's running through the outside tube from the sink over here, it never touches the water that's coming through right here. So definitely the water in the inside tube is kept separate from the outside. Now, as we're heating it, all of the water is taking off, and when the water is taking off, what we're left with is all copper 2 sulfate, and when we don't have water with our copper 2 sulfate, it goes back into the solid form. So what we get back is this blue solid. Now, the reason why we couldn't just use filtration with this is because the particles, the copper sulfate, are too small, and they would go right through the holes of the filter. Also, you can't just pour off the water when you have a solution of a copper 2 sulfate because that doesn't make any sense. You'd pour over the whole solution. You wouldn't try to pour the solution into another beaker and the copper sulfate magically stays behind and turns back into a solid. It just doesn't work that way. Alrighty, so another way that we can separate components of a homogeneous mixture is through chromatography. So we're gonna separate the components of this mixture by passing the mixture through a medium in which the components move at different phases. Now, the medium that you guys are gonna be working with is paper here. So there's different types of chromatography, like gas chromatography and other things I don't want to get into. But in this lab for 2A, we're going to do paper chromatography. So what we have is we have a piece of paper, and what we can do is we can separate the components of a mixture. And in this experiment, we're going to use dyes. So you can see here that we've used red and green, and what is this right here? Maybe black? I don't know. But anyways, we're going to separate the components by putting a little spot on a piece of paper of our dyes, and we're going to put it in what we call a chromatography chamber. It's just a little glass jar or a test tube. We don't have to get really fancy with paper chromatography. And then we're going to have a solution in here. And when we put the paper down into the solution, what it will do is it'll suck the solution up the paper. And the solution is called the mobile phase because it's moving. Okay. And the stationary phase is oops, I got these backwards. Definitely the mobile phase is the one that sweeps the sample up or over. Excuse me, bad teacher, bad, but we can deal with it. And the stationary phase absorbs the components. Oops, sorry about that. Okay, so the mobile phase is our solution. And the stationary phase is going to be the paper. Now, the dyes are going to be attracted to the mobile phase and the stationary phase differently. And if you have different components in your dye, like say we have the green dye and we would expect to have blue and yellow dye molecules making up a green dye, the yellow and the blue dye molecules are going to be attracted to the stationary and the mobile phases differently. And a lot of it has to do with their polarities and the polarity of the mobile phase and the stationary phase. And you'll get into a lot of that in general chemistry and organic chemistry. But just know that different molecules will move up the paper at different rates, and that's why we get the separation of those molecules, and that's why we can see the different components. Okay, so that's what you guys are going to see in the lab video when we do paper chromatography with a dye. You'll definitely see a separation. Alrighty, my friends, that is the end of this lecture, and I will see you next time. Bye-bye.